Hello everyone, my name is Serte Donderwinkel and I'm a PhD student at the University of Oxford. Today I'm going to tell you about joint work with Nian and Qi, in which we consider uniform directed graphs with an IID degree sequence. And we showed that the strongly connected components of such graphs converge under rescaling in the sense of metric space convergence. To make sure that we're on the same page, I'm going to give you some directed graph terminology. So in this example of a directed graph, we say that vertex 4 has in degree 3 and out degree 0. Now I'm going to draw the strongly connected components in this picture because we say that two vertices are in the same strongly connected components if they're part of a directed cycle. So if we find the directed cycles and draw them, then we find the strongly connected components. So here we see that a few cycles link up, and then we have a few trivial strongly connected components which consist of one vertex. So I will now show you how to sample a uniform digraph with a given degree sequence. So suppose we have these vertices and we want to sample such a graph. We say that we call these things out half edges and these things in half edges. And how we sample a uniform digraph with this degree sequence is, well, we pick one out half edge which we're going to start. We pick a uniform in half edge and pair them. So suppose that this one matches up here. Let's say we choose this one to be next in line, and suppose it pairs up with this one here. Let's say this one connects to itself, these link up here, and this one connects here. And now we see that we didn't actually sample a simple graph because we have a little loop here and we have a multiple edge here. But if we condition on these things not to happen, so no loops, no multiple edges, then the resulting digraph is uniform with the degree sequence that we started with. So now we're going to add an extra layer of randomness, namely we're also going to consider a random degree sequence. So we consider IID degrees where the in degree and the out degree of a given vertex can be dependent. And we condition on the total in degree and the total out degree to be equal, just to make sure that such a graph actually exists. So then we sample a uniform directed graph with this degree sequence according to the procedure I just showed you. And we write down its strongly connected components ordered by size, ordered by decreasing size. In order for a result to hold, we need some moment conditions. So the first moment condition ensures that this event is not a large deviations event. The second moment condition is the criticality condition, which I will get back to later. And the last condition ensures that we're in the Brownian regime, but I won't go into detail about that. So in order to describe what metric space convergence means in this setting, we need to define the topology. So firstly, we consider strongly connected components as metric directed multigraphs. And how we do that is by, for every vertex of degree 2, we merge its neighboring edges. So these three edges get merged into one edge of length 3. And then we define a metric on MDMs. And we say that they're close if there is a graph isomorphism that changes the length very little. And this is, of course, not very explicit, but what you should note is that asking for a graph isomorphism is quite a lot. So this is quite a strong sense of quite a strong topology. And then the result we prove is as follows. So when we have our strongly connected components ordered by decreasing size, and we rescale lengths by n to the minus a third, then we have convergence in distribution to a sequence of random strongly connected MDMs that are all 3 regular or loops. And this is a universality result, which means that the law of the limit object only depends on a couple of mixed moments, namely the ones that we needed to be finite. So 2 degree sequence of which the moments are the same will converge to the same limit object. So this is the first result on directed configuration model at criticality, but there are some results about off-critical cases. So firstly, Cooper and Friese showed the existence of a phase transition, which means that for a certain parameter, if the parameter is larger than some value, then there will be one giant strongly connected component with a positive proportion of the vertices. And for the parameter smaller than that value, the largest strongly connected component will have order log n, with n the total number of vertices. And in a recent paper, it was shown that in the off-critical cases, the diameter is of order log n, with again n the total number of vertices. There is one other result on metric space convergence of directed graphs, which is by Goldschmidt and Stevenson, and they consider directed Erdős-Rényi. And there's lots of work on the undirected configuration model, and in particular on the configuration model with IID degrees. There are the two papers that I mentioned. Because our result is the first result at criticality, it has some trivial corollaries that weren't known before. So one of the corollaries is that not just strongly connected components do not just converge at metric spaces, but also their total length and their total size converge on the rescaling, which is of course a weaker statement than the statement that we've shown. Moreover, our result implies that the diameter of the model is at least of order n to the third, which is of course in contrast with the off-critical cases where the diameter is of order log n. Moreover, we show that the Erdős-Rényi, the directed Erdős-Rényi model is in the same universality class as our model, and we conjecture that actually there are more models in this universality class. So a natural candidate, for instance, is the rank 1 inhomogeneous directed random graph. But we're probably going to work on that in future work. Okay, I will give you a bit of an idea of our methods. And for that, I would first like to recall how to sample a uniform graph with a given degree sequence, which was with the configuration model. And when I explained to you what the configuration model is, I said that it doesn't matter in which order we find bodies for the out half edges. So we can decide to do this in a depth first manner. So what does it mean? Well, if we start from this vertex, then this is the first one we pair, then this is the next out half edge, then this, then this, then this. So you see a sort of depth first ordering there. So that means that this out half edge is next in line, and it picks a uniform in half edge either from the stack, so one of these here, or of course it can pick one in half edge of a vertex that's already been used. But let's say that in this case, it connects here. And one thing to note is that this vertex is twice as likely to be picked next as this vertex, because the probability that a particular vertex is next in line is proportional to its in degree, because we pick a uniform in half edge. So that's something to keep in mind. Okay, so I already drew this in this exploration in quite a suggestive way. Namely, you saw a sort of tree shape there, and we make this even more explicit by defining the out forest. So let's say that this is the object that we get from sampling the configuration model. Then all of the edges that connect to previously found vertices are replaced by little purple leaves. So these purple leaves are kind of placeholders. We call this resulting thing the out forest. And one thing that you might notice is that even though there might be edges between different components of the out forest, well, this edge is never going to be part of a strongly connected component, because there are, by definition, there are no edges from this out component to this out component. So each strongly connected component will be contained in one of the components of the out forest. So that's a reason why we would want to consider these out components. Well, I promised you that I was going to give you a bit of a heuristic for what criticality means. And in discrete branching processes, criticality corresponds to the expected offspring size of an individual to be equal to 1. And of course, we don't really have offspring because we have a directed graph. But if you look at this picture, then you see that the number of children in the tree that we drew corresponds to the out degree. And as I argued before, the next vertex in line is sampled with probability proportion to its in degree. So you might, so if the stack is, for instance, very, very big, then so you don't really notice that you've already used a bunch of vertices, then a heuristic would be that the offspring is approximately distributed as the out degree biased by in degree. And if you believe this heuristic, then the expected offspring is approximately equal to the expectation of D plus D minus over the expectation of D minus, which we chose to set equal to 1. And therefore this is, so criticality of the strongly connected components corresponds to criticality of the out forest, if you believe my heuristic. And one last bit of terminology. So all edges which connect to a previously found vertex, so ones like this and ones like this, so the ones which we indicate with a purple vertex, we call them surplus edges. Okay, so how do we now sample the strongly connected components? Well, we build up the randomness in different layers. So the first step is sampling the out forest, and to sample the out forest, we need 2 things. Firstly, we need the order of discovery of the vertices, and secondly, we need to know at which time steps we add we go back to a previously seen vertex instead of finding a new one. So that's when we add a purple leaf. So if we have those 2 bits of information, then we're able to sample the out forest. Then secondly, I already told you that we don't care about all of the surplus edges. For instance, the ones linking up different components of the out forest are never going to be part of a strongly connected component. And we can come up with more criterions like that, which allows us to eliminate many of the surplus edges, which are a priori not going to be part of a strongly connected component. So we only need to sample the important ones, which we do. And then we cut up the resulting object into strongly connected components. And then actually the bulk of the work is showing that these 3 steps converge in the appropriate sense. And I'm very happy to speak to you about this later. And I'm also really looking forward to answering your questions during the conference. Thanks a lot for your attention.